In this problem, we're given an ordinary differential equation, x dot plus 5x equals 0, and one initial condition that x of 0 is equal to 3, and we want to solve this for the dependent variable x of t. And we're given that the independent variable is time t. We will be solving this using the Laplace transform method, although there are other types of methods available for solving this type of equation. If we look at the equation we're given, the x dot plus 5x equals 0, we can identify it as being a first order ordinary differential equation. It's first order because a single derivative is the highest derivative that we have, so first order. It is going to be linear. We have an x dot, but we don't have any x's squared, we don't have an x dot times an x, we don't have the square root of x or the sine of x, so everything is linear in this. And it's homogeneous, our right-hand side is 0. So the nice thing about using a Laplace transform to solve this is going to be that the initial condition that x of 0 is equal to 3 is going to be built right into our solution. So we're going to be able to find our total solution right away. Now in this case, we do have a homogeneous ordinary differential equation, so the homogeneous solution is the total solution. We don't have that non-homogeneous part or that transient part, but in future examples we will. So what I want to do is take my equation part, so I'll ignore the initial condition for the moment, and I'm going to take the Laplace transform of both sides. And I'll do this step by step for now so we see how each part is working. All right, so I take the Laplace transform of the left side and the Laplace transform of the right side. So a couple of things I'm going to be able to do is on that left-hand side, the Laplace transform of a sum is equal to the sum of the Laplace transforms. So I can split this into the Laplace transform of x dot plus the Laplace transform of 5x equals Laplace transform of 0. All right, so I was able to split that sum on the left into two Laplace transforms. So Laplace transform of a sum is the sum of the Laplace transform. And I can simplify this a little bit more. I have the Laplace transform of 5x, a constant like 5, I can take outside of that Laplace transform. So it's going to be the same as 5 times the Laplace transform of x. What I want to keep in mind here, I don't explicitly write it typically, but x is a function of time. I cannot pull functions of time outside of Laplace transforms. That 5 is constant, it's not going to change. But the x is going to be affected by that Laplace transform, as we're going to see in a minute here. Okay, so I did some initial simplification. Now I want to start to resolve these Laplace transforms. So if I go into my Laplace transform rules, let's look at the first term, that Laplace transform of x dot, so that first time derivative of x. That looks like what I have listed here as rule 12a. I'm going from the left side of my Laplace transform table to the right side when I want to go from the time domain into the Laplace frequency or S domain. So if we look here, this term is going to be this 12a. So f dot, or in this case x dot, is going to, when I take its Laplace transform, go to s times, this is going to be capital X, and I will say it's x of s for now, but in the future, typically capitalized variables are going to be functions of s, lowercase variables are functions of time. And then minus little x of 0. So this whole thing is that first term. The Laplace transform of x dot goes to the s, big X of s, minus x of 0. Now I can resolve that next term, that 5 times the Laplace transform of x. So if I bring that down, well, the 5 is just going to stay there, and it's positive. And Laplace transform of x, well, it's not on the table here, but if I just have an f of t, it's going to become f of s, which is the Laplace transform of f. So little x is going to go to big X. All right, so since I have a 5 here and I have s's, and it's a little bit tough to tell, I am going to put a line through s's just to make it clear what's an s versus what would be a 5. And on the right-hand side here now, Laplace transform of 0 is just going to be 0. Now, all the Laplace transforms have been resolved. So now I want to go on to my next step. Well, one, that x of 0 I was given, that's my initial condition, that's going to be 3. So I can rewrite that minus 3 plus 5 x of s equals 0. Now that I'm in the Laplace domain, what I'm trying to do is get, in this case, x, the dependent variable, by itself. So what I'm going to do is let me move the 3 to the other side. And now I'll have s times x. I'll stop writing of x for now, of s for now, plus 5x equals 3. And now I can take that x and factor it out. So s plus 5 on the left-hand side equals 3. Right, so to isolate the x, the next thing I can do is I can divide both sides by that s plus 5. Right, so now I have x by itself on the left-hand side, and on the right-hand side I have no dependent variables, I have constants, and I have s's. So that's the first thing I need to do to now start to go, and eventually I want to take the inverse Laplace transform so I can get back into the time domain. I'm still in the frequency domain right now. At this point we can look at the right-hand side and see, is it in a form where we know how to take the inverse Laplace transform? Now we have a fairly abbreviated table for our Laplace transform, so we might need to do some algebraic manipulation in order to make it look like something that's on the table, because right now it does not directly look like something that's on our table. The closest thing to our table right now is what's line 2 here. If we had something that's in the form of 1 over s minus a, that's something that we do know how to take the Laplace transform of, or the inverse Laplace transform of, because when we're doing the inverse Laplace transform, we're now going from the right side of the table to the left. We're going from s into t. So it's close. I can write it out what we're going to do. I want to take the inverse Laplace transform of both sides. So in this case, I just do that to both sides. And what I can do is that 3, because it's a constant, I can pull outside. So I can say this is 3 times the inverse Laplace transform of 1 over s plus 5 equals the inverse Laplace transform of, this is big X here. I'm still in the frequency domain, so just make sure that's clear, that's big X. All right, so what did this let me do? By manipulating this just a little bit, I have now 3 times the inverse Laplace transform of 1 over s plus 5. Now it does look like what we have on our Laplace or inverse Laplace transform table. If I say that a is equal to -5, then it looks exactly on the inside of that inverse Laplace transform. It's in that form of 1 over s minus a, when a is -5. So what does this let me do? The 3 will come along. Now I'm going to take the stuff inside, go from the right side of the table to the left side of the table, and this is going to be e to the a, which is -5 times t. And the left-hand side, the inverse Laplace transform of big X, this is why we wanted to isolate it, because when we do that inverse Laplace transform, that is just x of t. So now we've gone back to the time domain, and we have our solution for x of t. And what we get here is our total solution with that initial condition of x of 0 equals 3 built right into it. Just make sure that's clear. And if we want to test this out, make sure it agrees with our initial condition, x of 0. That's going to be 3 times e to the 0 power. Well, that's just going to be 1. So that is indeed equal to 3. So yes, our initial condition is satisfied. And we have come up now with that total solution, x of t equals 3 times e to the -5t. So again, to recap our steps here, I took that initial equation, the ODE we were given, I took the Laplace transform of both sides. I was able to split the sum into 2 Laplace transforms, or the sum of 2 Laplace transforms. Then I was able to take out a constant, and now I have things that look like what I have on the table. X dot is going to go to this Sx minus x of 0. This L of x, or the Laplace transform of x, just goes to big X because big X is, by definition, the Laplace transform of little x. And the Laplace transform of 0 is also 0. Once everything is in this frequency domain, then my goal is isolate the dependent variable, in this case, big X of s. So that's where it now turns into really an algebra problem of isolating that x term, which I now do here. So I got x equals 3 over s plus 5. Now, where I'm trying to go is to find the inverse Laplace transform, so I can go back from the frequency domain to the time domain. So I have to make sure that right-hand side is going to look like something on my Laplace transform table. In this case, with a little bit of algebra, I was able to rewrite it as the inverse Laplace transform of 1 over s plus 5, which does appear on the Laplace transform table. So then the last step, I can take everything back into the time domain and get my final answer.